Hi, my name's Julian Wood, and I'm a Senior Developer Advocate here at AWS Serverless. I love helping developers and builders understand how best to build serverless applications, as well as being their voices internally to make sure we're building the best serverless products and features. I've been using and talking about serverless for a number of years, helping the world fall in love with serverless, just as I have. Feel free to contact me anytime with your serverless questions, whether you have questions from today or other general questions around serverless development. Easiest is via Julian_Wood on Twitter. So, what am I going to be talking about today? I'm going to be diving deep into Lambda extensions, how they work, how you can use extensions, how extensions impact the Lambda lifecycle, and how the new container image format impacts packaging extensions. If we think of a traditional compute environment, it may have long-running processes, which start when a host, VM, or container sidecar starts up. An agent or tool that performs some work or analysis while it is servicing various requests. It may run for the whole time after an instance is started until it is shut down. If we had to have the same kind of model for Lambda, which is short-lived compute where you don't pay for idle, this would be wasteful, having a long-running process with intermittent invokes, which would cost more unnecessarily. And so we have released Lambda extensions, which is a new way to easily integrate Lambda with your favorite monitoring, observability, security, and governance tools. Lambda extensions are additional tools that you use to augment your Lambda functions and work within Lambda's shorter compute duration. You can add an extension to your functions to use existing tools to deeply integrate with a Lambda service to pull data out about function invocations. You can drop an extension into your environment and add some configuration information via environment variables to use or consume the capabilities of an extension. This helps to reduce function code and simplify your architecture, which is always a winner in my book. Extensions have a number of use cases, from observability and logging, being able to capture telemetry data not only during function invocation, but before and after as well. You can use extensions which automatically instrument your code, or use extensions to fetch configuration settings or other values before your functions themselves run. And hardened security agents can run as extensions to detect and alert on function activity. Extensions extend Lambda's invocation lifecycle to only run when there is something to do. They can run after a function invoke to send telemetry data about the invocation out, and can initialize and work before the runtime starts, and can perform cleanup tasks before the execution environment is spun down. There are a number of extensions and integrations already available from AWS and our many partners, and there are more to come. Extensions really makes it easy to use your favorite tools with Lambda. So let's have a look at how extensions work. There are three basic components of extensions. There are the extensions themselves and how you can add an extension into your environment by configuring the options in your functions. You can build your own extensions using the Extensions API to hook into the Lambda lifecycle. And extensions can use the new Logs API to get log data directly from the Lambda service. There's a lot more information about extensions available, so use the links and the QR codes to read all about it. You deploy extensions into your environment for zip archive functions by using a number of tools to add a Lambda layer to your function, and then adding some configuration information via environment variables to use or consume the capabilities of the extension. For functions deployed as container images, you can include the extensions within the image. This is built using the Docker CLI, AWS SAM, or the AWS CLI. Lambda then searches the opt extensions directory for both packaging formats and starts any extensions found. Lambda supports two types of extensions, internal and external extensions. Internal extensions allow you to modify the startup of the runtime process. They run in process with your code as separate threads within the runtime process, which starts and stops them. External extensions run as completely separate processes, but still within the same execution environment as the Lambda function. Having a deeper look at internal extensions, these allow you to configure the runtime environment and modify the startup of the runtime process within the single runtime process. Internal extensions use language-specific environment variables and wrapper scripts. This gives you a way to enable code to be preloaded during function initialization. Language-specific environment variables are set as part of the function configuration. And as shown here, for example, for Java, you can run a .jar file as a separate thread without modifying your function code. Internal extensions can also be used to auto-instrument your code in this way. For internal extension wrapper scripts, you delegate the runtime startup to a separate script. This allows you to, in effect, wrap your whole function up in a separate script. These are also configured via Lambda environment variables. Here you can see the function is configured to run a wrapper_script file, which manages the runtime process, and showing a code snippet from this wrapper script for Python, which adds the -x parameter to the runtime startup, which asks Python to add the import time command line parameter, which shows you how long each import takes. And you can use wrapper scripts in many ways to control runtime startup. An external extension runs as an independent process, separate from the runtime within the execution environment. You can see the process boundaries here. It can start before the runtime process and continue to run after the function invoke is fully processed. Because external extensions run as processes, as separate processes, you can write them in a different language than the function. We recommend that you implement external extensions using a compiled language. In this case, the extension is a self-contained binary that is compatible with all of the supported runtimes. If you use a non-compiled language, ensure that you bring your own runtime to the extension. Looking at resources and security now. As extensions run in the same execution environment as the Lambda function, they share resources with the function, such as CPU, memory, and temp disk storage. Extensions also need to be compatible with the associated operating system. And if an extension needs any network access, for example, you must apply network egress rules to the function configuration. In addition, extensions share the same IAM role and security context as the function. So the extension has access to everything the function has access to. And if the extension needs access to something, this must be included in the function IAM role. You can include up to 10 extensions per function, and these can be packaged in up to 5 Lambda layers for zip archive functions. And to do the math, you can package multiple extensions in a Lambda layer. Or for container image functions, you build and include the extension files within the container image. The size of your function's extensions does count towards the deployment package size limit. For a zip file archive, the total unzipped size of the function and all extensions cannot exceed the package size limit of 250 meg. For a container image function, this is 10 gig. And looking at performance, there are a few things to bear in mind with extensions. Extensions can impact the performance of your function because they share function resources such as the CPU, memory, and storage. For example, if an extension performs compute-intensive operations, you may see your function's execution duration increase. As extensions initialize before the runtime process starts, which must finish before Lambda invokes the function, an extension with a longer initialization time can increase the delay before the function is invoked, and this adds latency. Also, today, the function response is sent back to the client after all extensions have completed, whether it's synchronously via API Gateway or asynchronously via SQS, for example. So if you have an extension that takes a long time to send out, for example, telemetry data after the invocation, this can add latency to the function response. You can add more memory to a function, which also proportionally adds CPU and network throughput if your extension requires more resources. And during an invocation, the function and all extensions must complete within the function's configured timeout setting, or the function will error. To measure the extra time that the extension takes after the function invocation, you can use the new post-runtime execution duration function metric. To measure the increase in time and memory used, you can use the CloudWatch duration and max memory used metrics. And to understand the impact of a specific extension, you can run different versions of your functions side by side with and without the specific extension and work out the impact. For pricing, extensions share the same billing model as Lambda. You pay for requests served and the combined compute time, so this is the time that the function and all extensions run for. And this is measured in 1 millisecond granularity. So after all the explanations, it's time to have a look at an extension in action. We have a demo external extension which works with AWS AppConfig. If you're not aware, AppConfig is a systems manager feature that allows you to deploy configuration settings to infrastructure, including Lambda. What makes AppConfig super useful is being able to carefully introduce changes to your application that can be only tested with production traffic. And this uses robust deployment and testing capabilities to ensure your new configuration changes are deployed safely. The AppConfig extension runs as a separate local web process which caches information data from AppConfig and makes it available to the extension. Makes it available to the function. The function then makes a local HTTP call to retrieve the latest AppConfig setting from the extension. And this makes it super fast and doesn't require any AppConfig CLI command with the function. You configure which AppConfig setting to retrieve as a Lambda environment variable. Here's the link to the GitHub repository, which includes a number of extension demos. If you browse AWS samples and then to AWS Lambda extensions, you will find the AppConfig demo extension, which is deployed using AWS SAM, our serverless infrastructure as code tool. Jumping into VS Code, you can see there's an application which deploys all the components. This is stored in a SAM template. This consists of a Lambda function, and this runs Node.js 12 and has a Lambda layer attached, which is the AppConfig publicly available arm. And this is stored in the template as a configuration parameter. A SAM deploy then deploys all the infrastructure for the application, which I've run already to save some time for the demo, although it doesn't really take that long. We can see various AppConfig things deployed, as well as a Lambda function and associated IAM role. Jumping to the deployed AppConfig configuration. This is where you can configure a number of AppConfig features for doing those safe deployments. Here you can see I've set up a hosted configuration version, and I've used this to store a log level value of normal, which I'm going to use within the Lambda function. So jumping now to my Lambda function code, what this is going to do is this is going to return the event that's sent to it and whether it's a cold start and the log level value from AppConfig. The function has an environment variable configured which specifies that we want to use the AppConfig log level configuration setting. The extension has access to the same environment variables as the function. We can see the Lambda function has a Lambda layer configured. This was added during the SAM deploy and uses the AppConfig publicly shared layer arm. Now, remember, the local function is going to do a local HTTP call to retrieve the AppConfig configuration. There's no AWS SDK or CLI installed. It's just making a local call, which is fast, and the extension behind the scenes is caching the information from AppConfig. If I then do a test function invocation, which I can set up here in the console, and this is also, I could do something by testing it locally within SAM local invoke in SAM, and once the function is run, when I test it, we can see the log level return from AppConfig. And that's what we saw in the AppConfig console. And this is normal, and the cold start is true. If I run the function again, we see the same value returned from the AppConfig extension, but now the function cold start is false. It's doing its warm start. So heading back to AppConfig, I create a new hosted configuration version, and I change the log level to verbose. Once that's created, I go about deploying the change. I could use many features of AppConfig to test this all out safely, either using Lambda functions or various deployment strategies. I'm going to keep it simple and just deploy the changes immediately. So I can watch the deployment status until my deployment of the new version with verbose logging configuration is complete, and the current deployed version now switches to version number 2. So heading back into the Lambda console, I can run another test invocation. I can see now after it's run that the cold start, that the execution has seamlessly updated the configuration, and I now have verbose. But also notice there that the cold start is still false. This is a warm start. I've deployed a configuration change to a Lambda function without having to update the function with an environment variable and redeploy the function. For a single function, it would be easy enough, but think about how you can use this to update maybe hundreds of functions with a config change, maybe based on a metric you're picking up and not having to redeploy your configuration. And so the next invocation, even a warm start, gets the updated configuration from the Lambda extension. So let's look now at the changes to the Lambda Lifecycle and see how extensions running your tools can integrate deeply with the Lambda service. Before extensions, there was only the Runtime API, which provides an HTTP API for newer managed as well as custom runtimes to receive invocation events from Lambda. This is how functions receive events from the Lambda service and how they return function responses back to Lambda. The Runtime API is also what enables you to bring custom runtimes to Lambda. There were only 2 parts to control the execution environment within Lambda, the runtime and the function. Lambda initializes the runtime, which then initializes the function code outside the handler as part of the cold start. During an invocation, the runtime manages the function invocation, and the function handler code runs. The runtime is the part that handles the communication between Lambda and the function. When the invocation finishes, Lambda freezes the execution environment, so you don't pay for idle. When the next invoke comes in, Lambda unfreezes and reuses the execution environment, and this is for a warm start, and the runtime and function then carry on and do their work. With extensions, we're introducing the Extensions API, which builds on the existing Runtime API. Extension authors use the Extensions API to register for function and execution environment lifecycle events, such as invoke and shutdown. And in response to these events, extensions can start new processes or run some kind of logic. Extensions can now also use the Logs API to register for and receive logs directly from Lambda without having to go via CloudWatch logs. So we can see here how the init phase of the Lambda lifecycle is enhanced. When setting up the execution environment, Lambda searches the opt extensions folder and finds any extensions, and then runs them as those separate processes. And this happens before the runtime starts. An extension initializes and can do some kind of setup tasks. It then registers with an extensions API to tell Lambda what events it wants to receive. It then can complete other setup tasks, such as with the AppConfig example demo, running a local HTTP server and caching configuration settings. For an observability extension, this could be registering with the observability platform and starting to gather telemetry data. A log extension would start its log streaming receiver here. Then, the runtime process starts and initializes the function to run the code outside the handler. You can see Lambda manages the runtime process. You then manage the code and configuration of extensions as well as your functions as part of the function configuration. Then the function invokes. The extension can continue processing during the invocation, and Lambda freezes the execution environment when all extensions signal they've finished processing. It then unfreezes when a new invocation comes in for a warm start. You can see the extension can do some processing after the invocation to, for example, process telemetry about the particular invocation. If there are no further pending invokes, or Lambda needs to refresh the execution environment as part of managing the service, the runtime shuts down. And then the extension still has time to run final tasks before the execution environment is removed. This could be to send out any remaining logs or telemetry data, or notify or close connections to other systems. So you can see Lambda is exposing more of the function lifecycle with 3 distinct phases: init, invoke, and shutdown. And extensions can tap into these to allow your tools more visibility and control of the Lambda lifecycle. And there's a lot more detail in the documentation with great flow diagrams showing you exactly how the init, invoke, and shutdown phases work with extensions. There's also a useful and easy to deploy code demo in the GitHub repository if you're wanting to learn how to build an extension. This shows a custom runtime using the extensions API to take you through the full lifecycle of the execution environment, logging each step so you can see all the phases. So, with the option to package Lambda functions as container image, how do extensions fit in? Well, just to recap on container image support. Lambda container image support allows you to build and package your functions as container images from a Docker file. So you can take advantage of the rich container tooling ecosystem, including the Docker CLI. If you use container tooling to build applications, this allows you to benefit from the simplicity and familiarity of container development practices and dependency management. But you still get the operational benefits of Lambda, also with a larger deployment package size of up to 10 gig compared to zip archives, which are a maximum of 250 meg. You still get to enjoy Lambda's automatic scaling, high availability, start times of typically tens of milliseconds instead of seconds, native integrations with 140 AWS services, and only paying for what you use. Extensions are deployed to zip archive functions as Lambda layers. Lambda layers are not directly supported in container image functions, as images are created at build time. Remember, layers and extensions, when used in zip archive functions, are just files copied into the execution environment under /opt and made available to functions. So you can use Docker files to add the functionality of layers and extensions to your function container images. And there are a number of ways to add the files you need from layers and extensions to your container image functions. An extension publisher can have a container image format of a Lambda layer. So instead of adding an actual Lambda layer, you add the container image equivalent to your function build process. As Lambda layers are also just simply files, you can extract and copy the contents of an existing Lambda layer into your function image. You can also then repackage layer files, if you have those layer files, as its own container image. So this would be building an image container which just contains the layer or the extension files. And then you could share them as you would other container images. When you build your Lambda functions, you then add these container images to your Lambda functions during the Docker build process. As you can see here, a log extension image is added to a function Docker file, and then the files are copied into the /opt directory, which would then have an extensions directory containing the extensions files. And Lambda service would then search the extensions directory and would launch and run any extensions it finds. There's a blog post via the link which goes into a lot more detail on how to use the different options and how to use the functionality of layers and extensions with container image format. So, always nice to see this actually in action. I have a demo of a logs extension packaged in a function which is from a container image. The extension runs a local HTTP endpoint to receive logs directly from Lambda. This subscribes to receive platform and function logs, but not to receive extensions logs. This extension could be extended to filter, transform, or maybe process the logs in some way. In this more simple demo, the logs are copied to S3. The logs can be stored long-term for archiving or sent onto another system for analysis or troubleshooting. Again, you can try this yourself from GitHub. There are 2 versions, and I'm going to show the container image deployment demo, and you can link to the repo via QR code. I've got a log extension here which runs a local HTTP server, and I have the files for the extension which are stored locally, and I'm going to add them to a container image. The Python extension is going to write the logs to S3, and this is going to use the put object API call, using a Docker file to build the image for the extensions, and uses a multi-stage build with a minimal Python image to copy the files from the file system into the container image and manage the dependencies using a standard pip install. I can then start a new base image, copy the files and dependencies, and build a final image which finally gets pushed up to ECR. I then have a very simple Lambda function which is going to respond back to the client, and ultimately these function logs are going to be sent to S3. Now, looking at the Docker file to build my function, I add the previously created extension image and add the files from the image then into the function container image and set the Lambda handler. The function is then deployed using SAM with a package type of image, and this is configured with an IAM role allowing access to an S3 bucket created as part of the deployment. And there's metadata as part of the SAM template to say where the Docker file is and where the function code is located. And again, I've deployed this whole stack in advance just to save some time, but it's easy enough to do yourself. So heading now to the Elastic Container repository within the console, I can see there is an image uploaded for the extension, and I have an extension image. And there's also another image uploaded for the function, which includes the files from the extension image. Now, looking at the Lambda function itself, I can see there are no layers added, as you can't with container images. And the function has been built using the Docker file from the function container image I previously uploaded. Here's the S3 bucket name configured as an environment variable, which the logs extension uses to know where to send the logs. So I can go up and I can configure a test event and invoke the Lambda function a few times. The extension is going to do its processing in the background, and you can see when I invoke, I get a successful response, and go off and invoke the function a few more times. So if I then head over to the S3 console, I can see that the log files have arrived in S3 from the extension. The extension works seamlessly behind the scenes. The function doesn't in fact even know that the logs are heading to S3. I can open the file from S3 and I can see here the platform and function logs once it loads, but there's actually no logs within here from the actual extension, as I chose not to subscribe to these. So Lambda has sent the logs directly to the extension without going via CloudWatch, and you can use this to send logs to any custom destination. There's a lot more demo code on GitHub which you can explore to learn more about extensions. Look at the AppConfig code to see how you can use an extension. The custom runtime code shows how you can build an extension, and there are 2 versions of the log extensions, one for zip and one for container image packaging formats. And there's plenty more in other languages, including example extension wrapper scripts. And please feel free to contribute and add your own interesting examples. So, to summarize, I've been through how Lambda extensions are used to augment your Lambda functions, how you can more easily use your existing tools with Lambda for a number of use cases. With a simple installation and operational model, when using an extension, you configure options in your function configuration. I explained the difference between internal and external extensions, diving deep into the changes into the Lambda lifecycle and showing how you can influence them. And lastly, I showed how you can still use extensions in functions packaged as container images without using Lambda layers. See the QR code link for all the resources and more from particularly about this session on Serverless Land. For plenty more information on all things serverless, we have a super aggregation site, which I mentioned, called serverlessland.com. And this has got a whole lot of resources and blogs and videos and workshops and learning paths. It's really everything about serverless on AWS. So really, thank you. I appreciate you taking the time to watch today and hope I was able to help you understand how Lambda extensions can help you do even more with serverless. Please don't hesitate to contact me if you have any questions on Twitter @Julian_Wood. Thank you.